Log on, tune in, find out. Another good idea from Cambridge.
That's a good start. Well, thank you for the opportunity from John and others to speak, and thank you for him organising this great event. I had several motivations for giving this talk, and it was partly in the opening week in the workshop. We had several talks about stochastic parameterisation. So it was sort of in response to that, as someone whose some of his work corresponds to old-fashioned deterministic parameterisations, I thought it'd be interesting for me just to write down the process that I think we go through in building a parameterisation scheme, and maybe that'll help me think about where stochastic physics fits into that process. The title, I apologise, slightly murders grammar, but the we is me and Alan Grant, but it may be more general than that, but I wouldn't like to speak for the whole parameterisation community. Yeah, the picture here illustrates the process that I want to illustrate, the sort of generalities, and it was taken by Steve Monosmith. So it's an aeroplane going over the Great Lakes in Canada, and the wind's blowing up the page there, and there are waves, I hope you can see dark streaks that are propagating roughly in the wind direction. And as a result of an interaction, a dynamical interaction between these processes, we get things called Langmuir cells, which cause these strips to appear on the surface, that sort of foam and stuff collecting on the surface. So I'll be coming back to that image later. So the aims of this talk were to show how parameterization schemes can be put together. Chris?
Oh, shouldn't you wait for me?
I haven't said anything important yet. Which I will show again in a few slides' time. So given the breadth of the audience here, some of this may be a bit pedestrian, and I may emphasize things that don't seem important, but I think in practice are. Anyway, I apologize. I'll go quicker if I notice nodding anywhere in the audience. I think the fluid dynamics of the problem that I'm going to illustrate with is quite interesting, so I hope that will interest some of you. And as I say, towards the end, I want to raise some comments about where stochastic processes can come in, and they'll relate to things that Joe talked about this morning, and he talked much more in much more detail about them, actually. So looking around the audience, you all know why we have parameterization schemes. In an ocean model, for example, or Jonty's word, the ocean simulator, we solve the Navier-Stokes equations on a grid together with equations for the heat and salt content of the water. Because it's on a finite grid, there are unresolved processes. And I think there are three broadish categories of parameterization. First of all, there's the unresolved motion. So we have a grid, but there are fluid motions on a scale smaller than that grid that we need to represent. So 3D turbulent mixing and the clouds associated with their mixing are two examples of that. There's also the boundary forcing. Don't forget that the boundaries are not part of the equations. You have to supplement the Navier-Stokes equations with boundary conditions. So over the surface, the land and ocean surfaces, we need a surface energy balance, and that brings in new physics. And there are other things like missing orography that could kick off gravity waves. That was mentioned in Tim Palmer's talk. And then maybe the third category of parameterization, and I was thinking of Chris Huntingford, who isn't here today, unfortunately, when I wrote this one down, is non-Navier-Stokes physics, which we also parameterize. So an easy example of that is cloud microphysics. In order to make clouds do what we see them doing, we need to have droplets forming and freezing and all those other kind of complex things going on. And then one for Chris here particularly is the vegetation and carbon cycle.
So this is a blended atmosphere-ocean slide.
It is, I'm sorry, yeah. As you know, I work on the interface, 1 foot in the water or 1 foot in the air, if that's physically possible, Mike. Yeah. Yeah.
But obviously unresolved motions in practice are a lot more than just 3D turbulence.
Exactly. These are examples of, yeah, and I want to come on to that right at the end. Come in. So I'm going to give an example that relates to this one. I'm hoping that Chris Huntingford is going to talk later about how one develops parameterization schemes for that class. So I'll give it in a series of steps. And it's slightly dirty linen because I hadn't realised that we'd be filming this. So what we do is we identify a problem or a candidate solution to the problem. The causal nature here is not always clear. So I'm going to present it that there is a problem with models and here's a solution, but actually I've been interested in this problem for quite a while, so I had a candidate solution and I was looking for a problem maybe. So here are some errors in current ocean models. So here's the Hadley Center model, and these two panels here are showing global distributions of the ocean at 5 meters depth, so near surface ocean temperature. It's a climatology computed over some time period, and there's a dynamic range of sort of 0 down here up to 28 degrees, believe it or not, there. And this is an estimate of the error associated with that model run compared to climatology. And so what you can see is a fair amount of structure in the error, and that's of course a key point. Particularly there are large red errors indicating warm biases of 2 to 3 degrees in the southern oceans along here. And we're seeing cool biases in the northern hemisphere storm tracks here. So in the southern ocean, a warm bias tends to mean that the mix layer is too shallow because you've got a mix layer near the surface, and below that the water stratifies, so the water gets colder the deeper you go. So to cool the mix layer, one way of doing that is to mix more deep water in, thereby cooling it. So that's my potential solution to that I'm going to propose. Now you may ask, well, what about the cold biases up here? And this relates to what Hugo, Bob and Paul and I were talking about at lunchtime, which is the tuning of parameters in models. So as an aside to them, if you use standard parameters here, you actually get cold biases everywhere, believe it or not, but it's been tuned out to, there's a parameter, which I won't talk much about actually, that's been used to tune that out. In any way, we take there from the Southern Ocean at least that the mix layer is too shallow because the sea surface temperature is too warm.
There are already parameterizations.
Absolutely, absolutely, yeah, of course. Here's another example from the NCAR model, which Bill Large gave me, and this is showing a section down into the ocean here from the surface down to about 800 meters, and this is latitude here, with the Southern Ocean sitting in this band here and the equator here. And what this is showing is the observations of uptake of a gas called CFC. So CFC is very stable. They're the ones that are responsible for destruction of the ozone high up in the atmosphere above the southern pole. But they're very stable, so they can be used as tracers. And so the distribution of these CFCs within the ocean has been measured. And what you can see is it's mixed down in the vicinity of the Southern Ocean, and then it's carried along density surfaces. So the NCAR model has been used to simulate this process. The emissions of CFCs can be estimated reasonably accurately, and it's a well-mixed gas in the atmosphere. So you can provide a boundary condition to the ocean. And what you can see here is that the model gives a negative bias. So there's too little CFC being mixed down to this level. The white lines here are isopycnals, density surfaces. So again, it's consistent with the idea that the mix layer in the upper part of the ocean isn't taking the stuff deep enough. So the gas is ending up on the rum isopycnal, and that's messing up the mixing down here. So there are two pieces of circumstantial evidence that the mix layer is too shallow and needs to be deepened. So what I'm going to propose here as a hypothesis is that we need an additional deepening mechanism in the ocean. So here's an example where I'm not going to try and fix a parameterization. I'm trying to build in a new piece of physics which is not currently represented in the ocean model. And the piece of physics is these Langmuir circulations. So we've known about the basic fluid mechanical instability for quite a long time now. So there's a very nice sequence of papers by Craik and Leibovich from the 1970s, and they came together in 1976 and put their ideas together and wrote this great paper. What they show is that it's possible to have a fluid dynamical instability between the current in the upper ocean and an interaction with the effect of the surface waves that are propagating on the sea surface. So associated with the surface waves is a so-called Stokes drift. So water parcels go in circles as the wave propagates over the top. but the circle doesn't quite close, and due to a weak nonlinear effect, there's a drift to the right if the waves propagate to the right. And the magnitude of this drift decreases with depth. So this is called the Stokes drift. So an interaction between the Stokes drift and vorticity, which is angular momentum of water parcels, means that the angular momentum, the vorticity is carried with the Stokes drift, simple undergraduate fluid mechanics, and that tilts and stretches the vorticity into the horizontal, giving streamwise rolls, which are the origin of these Langmuir circulation. We've done a series of large eddy simulation, as others have, and I'll explain what I mean by that in a minute. And the schematic that emerges from that is that here's a region of ocean surface. These circulations live in the upper few tens of meters or less, 10 meters of the ocean. And we might have counter-rotating rolls here. And in between those, there's a region of convergence, which incidentally is what causes these lines of surface stuff to be collected together. And then that leads to a downwelling region associated with that convergence. So these downwelling jets remain really quite coherent at depth in the model. And so the hypothesis is that those organized downwelling motions are efficient, just a sec, at deepening the mix layer, more efficient than a random kind of turbulence would be. Pavel?
Can you remind what says the length scale?
The instability mechanism, like all, doesn't have a cutoff unless you put viscosity in, but viscosity here is not meaningful because the mixing is part of the turbulence itself. So for these strips, these are probably of order, I don't know, 20, 30 meters across. In fact, they widen with time, so there isn't a preferred length scale, I don't think. We can talk about that after. It's
the critical wind speed or something?
People say above 3 meters per second. Yeah, so anything above a very light breeze, and you should see these things. So next time you're on a plane, if you take nothing else from this talk, take a look out for these. You see them a lot. Okay, so we've got a potential error in a global model, and we've got a hypothesized solution. I should have said at the start that we haven't got to the end of this chain, so I can't tell you the answer that we've solved everything. So, but we're some way down the path. So the second step in designing a parameterization scheme is to figure out an idealized either modeling or measurement strategy that's going to provide you with the extra physics that you need to develop your scheme. So in parameterization of 3D turbulent processes, large eddy simulation is a tool that's pretty straightforward to use now. And there's been a nice history of people doing LES of this problem. So large eddy simulation, or LES, what we do is we consider a box of water. So this is about 250 meters on the side and about 100 meters deep. And we solve the full nonlinear equations of motion here, and we resolve almost all of the turbulent mixing. That's meant to be the idea. So we resolve time-varying 3D eddying motions, which are the turbulence, which we will then subsequently want to parameterize. So we solve the usual Navier-Stokes equation, time evolving, nonlinearity with Coriolis processes, pressure gradients. And we have to resolve the small stuff, parameterize the small stuff. So there are standard ways of doing that, which I don't really want to get into today, but it's kind of standard science in this field now. The novelty here, and what distinguishes this kind of mixing from a standard turbulent boundary layer, is this Stokes drift that we saw, which tilts and stretches the vorticity, giving us the mechanism of the Langmuir circulation. And it turns out that this leads to two new terms in the equations of motion here. So here is the Stokes drift tilting and stretching vorticity, and another source of vorticity on a rotating planet is the planetary vorticity. So the Stokes drift interacts on that, providing you consider long enough timescales. Hasn't been talked about much, I'll say it as an aside. This profoundly changes the current profile through the depth of the water, actually. It turns out to be a very interesting process, and I think of some significance in the global ocean. So again, for the cognoscenti, what we're doing in effect is a large eddy simulation of this so-called Crate-Leibovitz equation. So a standard LES, you chop that term out and you get a standard boundary layer. So the question we're asking is, with this new element in it, how different are things and how will it change mixed layer deepening and so on. So we take this box, we initialize it with a density gradient which is well mixed down to about 20 or 30 meters. We then apply a so-called thermocline, so a variation density and depth with colder water down at the bottom and warmer at the top. We start at rest. We blow a wind over the top, represented by a stress, which is uniform over this surface, and we apply this Stokes drift here. And we see what happens. These runs sort of overnight on a desktop PC, and we do a series of runs varying the wind forcing and the wave forcing via the Stokes drift.
So if it's resolving at a fine enough scale, why wouldn't it capture the Stokes drift?
Thank you for that. Yeah, what we don't want to do is simulate the wavy surface, because that gets very expensive. So by just parameterizing the waves as the Stokes drift, the top surface is a flat wall now. Yes, thank you for that question.
The equations are filtered in such a way that you don't get these waves.
Exactly.
Thank you.
Yeah, they're wave filtered equations. That's right. Okay, so we've got our tool. The next step is to use this tool to perform some simulations, and from that the goal here is to develop a scaling. So what are the dimensional control parameters that are important to this type of flow? So for a simple parameterization problem like this, it's sufficient to think about the length and velocity scale that are important here. So a natural way of doing that is to ask, what are the mechanisms for generating energy and dissipating energy within this turbulent flow? So written down here is the time mean energy equation of the turbulent motions. So there are two terms out at the beginning here which generate turbulent kinetic energy due to the mean shear. So if you've got pre-existing turbulence and a background mean shear, current shear, that will generate further turbulence. There's also a term which is specific to this problem, whereby if we've got turbulence and then this gradient of Stokes drift, that will also generate turbulence. So that's a new Langmuir type process. There's a buoyancy forcing. If you cool at the surface, that's going to drive convection. There's no convection in these problems, although we have done that, or we've thought about that problem. Here we've got some transport terms. So this term represents the movement of turbulence by turbulence itself. And this is the pressure transport of turbulence. And then finally, the dissipation. So ultimately, we know from Joe's talk that we're forcing at large scales here, because this is a 3D problem. There's an energy cascade down to small scales. Ultimately, the scales become so small that viscous processes dissipate the energy. In this problem, we put in an artificial viscosity, so this happens at slightly larger scales than the real ocean to make it tractable. So then from the large eddy simulation, we can compute these terms and their profiles to establish the dominant balance in this equation, and from that we'll gain the length and velocity scalings we need to characterize this process. So first of all, here's the shear production. If this were a standard wind-driven mixed layer, that would be a big positive term, but it's small here. By contrast, this Stokes production term is a big term here. So that's just the tilting and stretching of vorticity mechanism manifesting itself in the kinetic energy of the small-scale fluctuations. The dominant balance to the production is the dissipation. So we're producing via this tilting and stretching, and then we're dissipating to heat. However, the transport term is also important. So we're removing energy from the upper regions here, and we're adding it or transporting it down into the bulk of the mixed layer. So this is really the LES showing us that schematic that we've got these rolls near the upper surface, and in the convergent zones we've got the downwelling regions transporting the kinetic energy down to the base. And here's the base of the mixed layer, and you can see we're transporting plenty of turbulence down there to then deepen the mixed layer, and I'll come on to that in a minute. So the way, and this is common to almost all boundary layer parameterizations, the way we get a scaling for this is that we try and determine the dominant balance. Dissipation is important. The dimensions of dissipation are a velocity cubed over a length scale. So we're going to want to determine this velocity scale. What does it depend on? So I'll call it W star L for Langmuir for the time being. What you can see here is that although the production of energy is restricted to the top layer where the Stokes drift acts, because of the turbulent transport, it's then distributed over the whole depth of the mixed layer, which is small letter h. So I'm going to hypothesize that the length scale of this turbulence is the mixed layer depth, h. I can then estimate the dissipation to be W star L cubed over h, and I can balance that with the production by shear when redistributed over the depth, put that together, and I get a velocity scale that depends on the wind forcing and also the Stokes drift in this well-defined way. A number that appeared in the literature from Jim McWilliams and Pete Sullivan is this Langmuir ratio, or Langmuir number, which measures the wind forcing compared to the Stokes drift. They put a square root in there, and if you'd like to just tell them, Joe, it's incredibly inconvenient, that square root. Yeah, that would be really helpful. It'll make some of our later things look much messier than they really are. So what this demonstrates are that we now have a length and a velocity scale which we think characterize this kind of mixing, and that will form the basis of our parameterization. We also have a dimensionless number here which we believe, or which we think we've shown, controls the relative importance of the wind to the wave forcing. I'll put some flesh on that bone in a minute. So we've got a large eddy simulation. Where do observations come in? And this is another important point I wanted to draw out. At what point in developing your parameterization do you bring data in? Because you could build a differential equation, put it in your GCM, run the climate and say, does it improve it? But that's a rather delicate or indelicate way of testing a new parameterization. So instead, what we do is to plot quantities out of the large eddy simulation. So let's start with this one. So this is the fluctuation in the vertical velocity variance. So we plot this because it's something that can be measured in the upper ocean using ADCPs, for those who know about those things, and such like. And we've normalized this variance of the vertical velocity. Remember, the mean is 0 because it's a horizontal box and there's no up or down forcing. So there's only fluctuations in the vertical. We normalize it on this scaling velocity. So if we've got the scaling velocity right, the profile of this with depth, when normalized on the length scale, h, should have the same form for any type of Langmuir turbulence. That's the whole point of the scaling. It's also the power of the scaling. So what you see here is a whole bunch of simulations with a whole range of values of the Langmuir number, and the collapse isn't perfect, but it's pretty fair. And you also see measurements here of the same thing, normalized in the same way, showing pretty good agreement. So that's the point where we can say that this reduced model of the mixed layer is good for simulating this kind of ocean mixed layer. And therefore, we can use the results now to build a parameterization that we have some faith in. Do you see the logic? We've used the observations to test the LES when viewed in the scaled variables. So the observations are helping to verify the scaling and also the LES in producing the similarity profiles.
So what observations are those?
Yeah.
Isolate this,
I was just about to start a new paragraph about that. That's a good question. These observations make the agreement look fantastic. And as you know, Henk, I'm just writing a proposal for a cruise out to sea to make measurements. So why would we need that? The reason is none of these, well, very few of these measurements measure the Stokes drift, the wave properties. So there are 4 or 5 different observation sets here, and in each one, we've tuned the value of the Stokes drift to optimize the agreement. Hence, we need a cruise that makes co-located measurements. So the observational support for this is incomplete at the moment, I would say. The best we can say is we're getting the shape right, but I can't say that the scaling is right. So actually there's an open question here. Does this filtered form of the LES reproduce the physics adequately? We don't know for certain yet. A second piece of evidence about the scaling comes from this plot. So this is, again, a vertical profile, this time of this dissipation rate, scaled in the way you'd expect from the scaling, so epsilon h over w star cubed. And these are simulations for different values of this Langmuir number. So large values of the Langmuir number relate to strong wind forcing or low wave forcing. So that's a standard shear layer, so it's right out here. As we reduce the Langmuir number, we're increasing the importance of the waves relative to the wind forcing. And what you see here is that you do see a collapse with some scatter, of course. It's real data, real LES data. Trip of the tongue there, gave a lot away. And for Langmuir numbers less than about 0.5, we get a reasonable collapse here. Now again, this for a parameterization building exercise is really a key step, because what it shows is that there is an asymptotic regime of the turbulence when this scaling collapses the data, the LES data. And that suggests that this Langmuir state is an asymptotically different state of the turbulence to shear turbulence. And therefore you parameterize it in a different way to shear turbulence. It's just different. And the fact that it collapses onto this tells us there's a new asymptotic state. Another way of seeing this is if we plot the dissipation at the middle of the mixed layer versus the Langmuir number. So again, wind forced out here, wave forced out there. This is the usual value you get for shear-driven turbulent boundary layer. As we reduce the Langmuir number and increase the wave forcing, we get a dip in that and then a rise. And the rise is consistent with this scaling. So there's a different regime when the dissipation follows that scaling, telling us it's a distinct asymptotic regime. This may sound like semantics, but what it means is we parameterize it as a distinct boundary layer or mixed layer type, rather than taking the shear boundary layer scheme and trying to tweak that. We sort of start from scratch, and actually that's better, easier to do. I'm sorry?
The intermediate numbers give you a problem, right? You can't just interpolate from one to the other here.
You can't, but that's what you do. So, so that's a straight interpolation. What's happening here is it's an interesting problem. There's some calculations we can do here that we haven't finished yet. Sort of more simplified analytical approaches. You're beginning to get the roles, but they're not firmly established. And what's happening is that that's wiping out the shear that you'd normally get in a shear boundary layer, and that's reducing the dissipation. So yeah, there's an interesting intermediate. But Bob's hit the nail on the head. So what you do is we've got our distinct shear state and our distinct Langmuir state. What you do in practice in a parameterization is interpolate. And it is possible to interpolate with a dip in the middle as well as without, of course. But that's part of the sort of gory details of the parameterization itself. So we've got a scale.
Yeah, just one more point. So would the justification of that be something like that there over the grid box or wherever we're employing parameterization, there would be some variability in the wind? So it's not that these things are happening at the same time when you're interpolating. You're interpolating the effect because you've got some where it's sort of windy and somewhere it's wave force.
No, in the form that this is phrased, you would be assuming your whole grid box is one type. It's just the mechanics of how you actually, you'll see it a little bit more explicitly in the next slide or the one after that. You end up with eddy diffusivities, and you've got to have those smoothly varying. So you can't jump from the shear state to the Langmuir state without a smooth interpolation, otherwise your model doesn't like that. Joe.
One other thought along those lines. Is it true to say, is it right to say that under those circumstances, the functional dependence of the turbulence is much more complicated combination of shear turbulence and Langmuir turbulence, in because of that, it's very difficult to say exactly how those two functions need to be.
Yeah, that's a fair comment. Yeah, the in-between is not quite as simple as you'd like it to be. We're showing dirty linen. It turns out that many of the other properties do interpolate smoothly. The dissipation is actually, so things like this variance do just interpolate, and that will be helpful soon in a minute as well.
What's the typical range of values of the Langmuir number?
I'll come to that at the end. Yeah, that's also a key question. So now we've got some data from the LES. We've got a scaling to organise that data. We now have to go into the gory details, and I'm going to not go into the gory details. I'll try and give you a flavour that on the one hand shows the amount of empiricism that's in there, but also shows that there is a limit to the empiricism. That's the fine line I'm going to try and leave you with here. Just to remind those of you not familiar with these kind of things, what we solve on the grid are the mean, momentum and buoyancy equations. So buoyancy is a combination of temperature and salinity, giving the effect of the density on the flow. So we've got resolved flow U and V, the horizontal wind components, the tendency of those and the Coriolis effect, and then the gradient of the turbulent stress. And the turbulent stress is the bit that we're trying to get at from the parameterization. And then in the temperature or the buoyancy equation, the tendency of the resolved scale buoyancy is also a result of a divergence of turbulent fluxes. So we need to also parameterize this turbulent flux. So these are just the kind of things that were, they're relations to what's appearing in here, and that's why I focused on that TK budget. Okay, so how do you do that? Well, let me give you a flavor by considering the buoyancy flux. I can talk more about this privately, but I want to get onto some other things. So it's possible to write down the equation for the buoyancy flux and its tendency without approximation. So for this simplified geometry, that's what it is with the Stokes effect. So the tendency here, which is 0 in these experiments because we've integrated to statistically steady state, has these terms, and they're related to the terms in the turbulent kinetic energy. They can be interpreted in a similar way. So there's a gradient-like term. So if you've got vertical motion acting on a buoyancy gradient, that transports flux, or that carries a flux. There are transport terms here. So these are redistribution. They don't generate or destroy. They just spread it around, because if you integrate over the whole domain, you've got 0 flux at the top and bottom. So this is the turbulence carrying turbulent flux of buoyancy. And this is Stokes drift, bizarrely, carrying... I don't understand that term just at the moment, so don't ask questions about that. There's a buoyancy creation of buoyancy flux. Okay, you've got buoyancy, you make convecting motions, and that carries a flux. And then there are these pressure correlations. So this is as far as we've got. You use the LES to compute the profiles of that. We can use the scalings to normalize those, and we then believe that these are generic to Langmuir turbulence. So these are the shapes for Langmuir turbulence, okay? And given these parameters, we can plot stuff on that, and that's the way they look. They're universal, if we want to be bold. Not just Earth-like, they're universal, okay? Yeah. No, I didn't write it down, but yeah, buoyancy, salt and temperatures, both in, yeah. Okay, so the approach that we take now has been well tested in the atmospheric boundary layers. So Bert Holzlag and others in the Netherlands pioneered this approach. And the kind of thing you say, we haven't got there yet. So the kind of thing you say is that the I haven't labelled these, have I? Yeah, the transport term, which is that one, looks a bit like the production term, which is that one, but offset. And it's offset by a constant when plotted in the normalized form. So let's see. So that one, the blue dotted, and this one have a similar shape, but they're offset by a constant. And that's not quite right. It works better in a dry convective boundary layer over the atmosphere. But this is the kind of thing you do, okay? You then say that this pressure correlation, and there's a lot of theory been developed on this because it's not obvious what that does. Turns out there are two generic processes captured in this. One is a so-called slow process, whereby the pressure returns things to isotropy. So pressure is an isotropic force, and any preferential direction, it tries to smear it out. So there's a classic parameterization of that part that goes back to Rotter for the cognoscenti, which just relaxes things down to isotropy, and that's what that does over some time scale, tau. And tau, guess what, we'll get from the scaling with a coefficient in front of it. And there's also a so-called fast bit of this, and those of you who know Julian Hunt pioneered rapid distortion theory, which is a linearized theory of turbulence, which enables us to compute these kind of terms. So again, we can say with some theoretical confidence that that's a good form for that, with a coefficient in front of it. So I've not talked about that term, I've not really talked about that term, but if I put those bits together into this, remembering that the tendency is 0, I get that the return to isotropy, which is the flux I want, divided by the time scale, is equal to the gradient part plus a constant part. Now if you move the tau up to there, this bit then looks like an eddy viscosity, a gradient transfer, with the eddy viscosity given by the vertical velocity fluctuations and this time scale. So people often talk about eddy viscosity models as if there's no support for them, and you just put a viscosity in. So here's a procedure that you may not like, because there are some empirical things here, but it is a defendable and testable hypothesis that gives you an eddy viscosity that you can go out and measure, or you can infer from your LES. Okay?
A mathematical test for this. So you're saying you're predicting average quantities.
Yes.
And you know that because you're dealing with bounded quantities, they will stay smooth. So if your subgrid model is correct, the equation, including the subgrid terms, will have smooth solutions. So does that work?
Does this have smooth solutions? It's a numerical solution, so how would I...
You can tell if you solve it numerically whether it's trying to misbehave or not, because a lot of parameterization used in the atmosphere actually will misbehave.
Yeah, no, the LES doesn't blow up.
Well, the LES doesn't, but then you take this model into larger scale.
Well, I haven't done that yet, so I can't tell you the answer, unfortunately.
That's
Yeah.
one of the things you can test,
Yeah,
but you
yeah.
know it's the correct subgrid model.
Yes,
Those equations must have smooth solution on the averaging scale,
yes.
and
Yes.
that's something you can test. It
That's...
doesn't say you got it right.
No.
It tells you it's criteria.
Yes. That end of it you will want to comment on later, Mike, because that's where I fizzle out, but Joe.
Yeah, so this kind of relates to the discussion this morning also, in the sense that this is a second order closure scheme,
Yeah,
basically.
yeah.
And in the end, you need diagnostic relationships.
Yeah.
And in the same way that in balanced motion versus unbalanced motion in the atmosphere, for example, the diagnostic relationships can misbehave at times.
Yes.
This is one of the difficulties, right? Because
Yeah.
you actually have to close the system at some level.
Yep.
Here, and this is where a diagnostic relationship inevitably
Yeah.
appears.
Yeah, that's right. Agreed. Okay. With these elements, there's also a constant here, and so there's a constant flux given this Langmuir, and this is really representing those downwelling jets. It's how those appear in the parameterization, and you get them as they pass the updrafts in the convective boundary layer. So we're expecting the parameterization to look something like that. We can use the LES results of the W squared with the scaling. We have a profile earlier. You just fit a functional form to that. So that's the sort of ugly side of parameterization schemes. So we're getting some coefficients out here. If we choose to do it this way, and again for the experts, this is how the KPP model works, which is the one that's used in the ocean. You then fit functional forms which determine your eddy viscosity profile. But again, at least it's measurable quantities. Okay, now this is the step that is the really hard step, and you're all laughing. Mike's colleagues at the Met Office and Joe's at NCAR have limited resources, And they have tons of people clamoring at conferences saying, my process is the most important thing and it'll solve all your problems. And they just don't believe you. And
then they'll do an experiment where they double the time step and solve all their problems.
yeah, oh, Mike, that's harsh. Well, it does, but Glenn Schutz also showed a plot at the end of his stochastic physics talk showing how model skill had improved through improved physical parameterization compared to stochastic physics. So I know where I'm putting my effort just at the moment. So in the spirit, it's actually Paul's question earlier, how important is this in the ocean? And this, I think, is an important step. And with the data sets we have now, it's much easier to kind of think about this. So what we've done here is to make climatological plots of this Langmuir number from the ERA 40 data. So ERA 40 for the non-experts is 40 years of gridded data in the atmosphere and at the sea surface every 6 hours that's been produced by a combination of measurements and the European Centre forecast system, a sort of synthesis of that. So in some sense, it's our best estimate of the atmospheric state over those 40 years. So what we've done, so that's got the wave information and the wind information, so we're able to compute this Langmuir number. Remember, that's the U star divided by the Stokes drift. We've then split the Langmuir range into these 4 bands where different behaviours happen. So we've got the total shear one out here. We've got the mixed one in here, and that's where we had the dip in epsilon that we had the discussion about. We've got a band here which is sort of pure Langmuir, and then we've got a sort of extreme Langmuir. If you like your extreme sports, this is extreme Langmuir out here. And what these plots are showing are the frequency of occurrence of those bands during, I think we did this for 5 years as it happens, averaged over all seasons. You make seasonal plots, obviously. And the first observation is that, blimey, our classical shear-driven Ekman layer doesn't seem to be important at all. You can't see the colours here. That's 0% and that's 100%. So the best we're getting here are the yellows, which is up there, but these are really very isolated spots. So according to this parameter and according to this data, you don't get what people thought was the classic mixed layer, which is wind-driven sheared turbulence, which is there, okay? It doesn't exist in the ocean. The ERA data, oh, you tell me, I can't remember.
You don't start thinking about lack of resolution when you make that sort of comment.
Okay, as usual, I've overstated it.
If they hadn't put the square root in, you'd have to use more digits on your plots.
Yeah, that's right. Where most of the data sits is in these 2 intermediate bands. So this is the mixed band here of shear and turbulence. And you can see that in the tropics and extratropics, that seems to be prevalent. But what I haven't talked about is convection. Again, this is speaking perhaps to the experts a little more. Convective ocean mixed layers are rather important in this part of the world. So the comparison we have to do there is to compare the Langmuir with convection. So that's the plots that we're just making right now. It's less clear cut, but it's definitely still important.
So you're essentially using this as truth, saying how
Yes.
regimes now. Does the resolution strongly affect your calculation of the Langmuir effect?
Yes, that's right. So if I had high frequency fluctuations on wind speed or wave speed, would that affect this?
I think you magically go an ERA 40 with a 1 kilometre grid and a very high vertical resolution, would you've got a very different picture for that calibrated truth plot.
I wonder whether the time resolution might be more.
Well, that's right. It's 6 hourly, so it's certainly picking up the mid-latitude storms.
I'm just wondering whether you're actually got a realistic estimate of that regime or not, because it's not really there in the low resolution model.
Yeah. Well, you need the stronger wind speeds at a time when the waves are lower. That's what you need. So you need to be picking up the frontal regions. That's where you'd expect it synoptically. So on that basis, I guess I'm prepared to concede some light blues to you up here, but I don't know.
I think it's not a big shape picture like that.
I think, no, I don't think so. I don't think so. I mean, it's a good thing to think about. I can't really answer with any great confidence. The regime, which seems to be important, notwithstanding Mike's comments, in the mid-latitude storm tracks, so the regions which are windy in the world, the southern one here and the northern storm tracks here, seems to be this band where we're firmly in the Langmuir regime. So you'll notice particularly in the Southern Ocean where we were seeing those warm biases in the sea surface temperature and in the mixed layer depth from the NCAR model. Again, compared to convection, the Langmuir seems to be a very important component, but that's a very important test.
In the Langmuir shear regime, the equatorial Pacific looks like a region where it might be important.
Yeah.
You have ocean moorings and
Yeah.
do they demonstrate? Have you looked at that data at all?
Some of the data have we looked at the tropical ocean mooring data? I don't think any of the data I had on the previous plot was from that. It would be worth investigating that. Yeah, that's a good question. Yeah, no, I don't think that did show up in the previous. You're thinking of the Togara way.
It's probably accounted for in the ERA analysis.
Yeah.
But at least in terms of the surface winds. But the question then is how realistic are the surface wind products that are coming out of the analysis?
Yeah, sure.
That's another question.
Yeah. Don't forget, the only reason we're doing this is to persuade these dullards.
Yeah.
Oh! Can you turn the microphone off now, please? No, I mean, yeah, it's not the only reason. And these are all perfectly justifiable questions. I mean, I think the only defense is that for global coverage, this is probably the best data we've got at the moment. It would certainly be nice to zoom in on some regions and get a higher resolution look. Let me just, so in order to, the case we've been making to Met Office and so on is this is the so-called entrainment rate at the base of the mix layer. So this is the turbulent mixing at the base of this mix layer, which drives deepening of the mix layer and thence the cooling effect that I was proposing at the start. Plotted on this axis, normalized in the way it's usually normalized for standard shear turbulence. And then this is the Langmuir number going from the shear, the mixed, to the pure Langmuir out here. And really the point is that in this mixed regime, the entrainment rate is almost unchanged by the Langmuir, and it's partly associated with that dip actually in the epsilon and the loss of turbulence there. But that's good, because we don't want to deepen the mixed layer in these regions because the current model's doing okay there. If you go to the Langmuir regime where the Southern Ocean and the Northern Storm Tracks are coming in, so that's this regime here, this is a log-log plot, so those points are a factor of 2 to 3 bigger than we'd be getting in the shear driven. Now 2 to 3, I don't know, to people outside the field, 2 to 3, come on, all this work, 2 postdocs for 6 years now. 2 to 3 is a fair bit, you know, you deepen twice the amount if you apply it for the whole period. So a factor of 2 to 3 is a fairly big number in this context. Okay, so really that's my story on this so far. We are looking to spin up a program. The UK funding agencies have just announced a call in this topic to go to sea and to develop some parameterizations and indeed demonstrate that all problems disappear. But I hope I've shown you sort of the steps that we've gone through. I hope I didn't get too bogged down in detail and give you some indication of where the empiricism comes in and where the more precise stuff comes in. I thought it'd be interesting to try and tie this more directly to one of the themes of the work of the program, to say what you might call the school teacher problem. So if you're a school teacher, and this is why I'm not a school teacher, there's always a noise in class. And your problem as the school teacher is to say, where's the noise coming from? So here it's really easy because it's usually Mike Cullen and it's, you know, been other serial offenders today. But in the stochastic framework, where might noise come from? So I thought it'd be interesting just to see if we can categorize those. And these are really just thoughts collected over the last few days, so I hope they're not too banal, and I think we can relate them to Joe's talk earlier. So a clear one is in the interaction of the resolved with the unresolved fluid dynamics, so related to what I've been talking about here. A second one is sampling error. So Bob Plant in the workshop talks about a nice piece of work where what I showed here was us parameterizing time mean fluxes. So this is long time averages. Supposing we ran the model at such high time resolution that we were beginning to see the statistical sampling fluctuations around that long time mean, we would have that would come in as a stochastic process, obviously. And in the convection problem, it's surprising how big the grid can be and still have this sampling error. Bob was showing us that even at 50-kilometer resolution, there are sampling issues about whether you have enough clouds in your box to overcome that. What's really nice about that, and we've talked a lot about this over lunch and so on, is that you can see that you could make a parameterization there that knew about the size of the grid box and varied the amount of sampling error it put in depending on the grid box size compared to the size of the process. And that in a way is one of the themes that I'd like my community perhaps to think more about, is parameterizations that know more about the grid scale that you're solving them on, rather than just assuming this scale separation.
Gravity wave drag schemes do that rather simply by knowing how much subgrid scale robbery there is.
Yeah. Yeah.
Demonstration that that works.
In fact, that's my example for this last one, which is missing detail in boundary forcing. So we've got a grid which resolves some of the mountains, and so those mountains that are actually resolved, the wind blows over them, you kick off gravity waves that propagate up in the atmosphere, a very important part of driving the circulation. But there are smaller scale mountains and hills that aren't represented. There is smaller scale variability in the winds that will kick off gravity waves as well, and we don't know how much power is in that. And there are other examples of that. Paul Williams in his talk in the first week talked about the stochastic arrangement of precipitation within a grid box, giving stochastic freshwater forcing into the ocean mix layer, and showed that played a role in deepening the mix layer as well. Let me just say in my last slide a little more about the fluid dynamics mechanisms. So I guess what I'm trying to do here is see how the stochastic forcing comes out in the way that I'm used to looking at things. And I apologize if this is obvious to everyone. It wasn't blindingly obvious to me, although there's a very nice paper written by John Wingard called Numerical Modeling in Terra Incognita. So if you remember, in old maps of the world which were unexplored, you'd write Terra Incognita, unknown lands. So this is the place, here be dragons. And I'm absolutely certain that's what John wanted us to think when we read Terra Incognito, here be dragons. So what I'm writing here is largely taken from his paper. So suppose we resolve some of the fluctuations. So to make the connection, I hope, with the previous stuff explicit, we'll divide the velocity into three components: the long-term time mean current, say, and this could be the global seasonally average jet structure, if you like, it doesn't really matter. And then a resolved fluctuation, which could be a turbulent fluctuation, it could be one of Joe's QG turbulent things, or it could be a 3D turbulent. And then a subgrid scale. So we apply a filter, and that filter could be a wave number cutoff filter or a Gaussian, but it represents what the grid is doing to your Navier-Stokes equations. If you then filter the Navier-Stokes equations and form energy equations for the resolved and the subgrid scale parts, you get this. So these are cousins of the turbulent kinetic energy equation I showed before, only in that case I didn't resolve any of the fluctuations. So the cut was between long-term average and all the 3D turbulence. Here I'm keeping some of the randomness. So what you see is, as we saw before, turbulence against a mean gradient makes more turbulence. There are transport terms, as we had before, but there's also a transport term associated with interaction of the resolved and the subgrid scale. So this unresolved process, firstly, redistributes energy and presumably momentum and flux. So that's a potential source of stochastic forcing. And then there's this interaction term, and I'll come back to that in just a minute. If we go now to the subgrid scale and form that energy equation, remember this is the one that we need to compute and therefore parameterize that term and that term if we're going to successfully run our GCM or weather forecast model. And we might get inspiration for how to parameterize these by looking at the subgrid energy. That's the logic as we did in the parameterization scheme. So subgrid scale looks very similar, very similar. There's another redistribution term. It looks slightly different. It's sort of redistribution of mixed energy. So there's resolved subgrid, which forms a mixed energy, and then another component mixes it. So it's quite a hard term to get your head around. It would be nice to have a toy model that just gave us some intuition. Maybe some of you know of one about how that works. There's this interaction term, which is the direct coupling between these two, and then there's the dissipation as we had in the turbulent kinetic energy. And the interaction terms look like this. So they're similar in form to these production terms here, in that they're a stress, a Reynolds stress or a momentum transport acting on a strain rate. So here Sij is du by dx, the tensor. So it's the classic energy production term. It's a stress acting on a strain rate. And the interaction term is the difference between the resolved winds or currents acting on subgrid scale stress with the subgrid scale winds or currents acting on the resolved stress. So they're both mixed, and you can see that it takes from one and adds to the other. The sense of the sign has to be such that it takes from there and adds to there in order to supply the dissipation, because in a homogeneous flow all these disappear and you have to, that's a technicality maybe. So in 3D turbulence it's possible to do simulations and then compute these terms, and I don't know, question to you guys is whether this has been done in other types of turbulence. I'm sure it has. What you find is that there is a net drain of energy going from the larger resolved scales to the small subgrid scales. So that's part of your energy cascade and the energy dissipation. However, if you look on fine time scales, there's enormous fluctuations in that number, so that not only the magnitude but the sign changes. So in fact there can be a backscatter of energy from the small scales to the large, and then from the large to the small, and it's the net long-term residual which represents the drain down to the small scales. And no, it's the strain rate. There's no entropy in this side. The strain rate, dui by dxj. Yeah, yeah. No, it's just a strain rate. To get these out of the equations, you have to do a lot of tinkering. There's some vector calculus involved. I think I'm pretty confident about those, but I'm not sure I could do an Andrew Stewart and write it out on the board right now. Yes, Pavel.
What's the advantage of formulating what you formulate here in terms of energy, which is quadratic quantity,
Yeah.
rather than direct in terms of U? Then you will have not cubic.
Well, the reason you go into quadratic terms is that those are the terms you're going to have to parameterize, because those are the terms that come out as part of your closure thing, right?
We don't solve typically equations for energy, we solve equations for just energy.
Yeah, I guess I'm just looking at these to see what inspiration we can get in wanting to parameterize the in the mean momentum equation the stresses that are unknown. So I'm not necessarily advocating solving these. I'm just saying these are providing inspiration for where the backscatter could come from. So there are some trivial observations for this, I think. The first is that the potential sources of stochasticity are additive. So you don't chuck out the hard-won parameterizations that have been developed before. You need to add noise. And the way the noise occurs, is it multiplicative or is it additive? Is difficult because it's wrapped up here, but it's almost certainly non-multiplicative in the sense that that's resolved with some random strain rate acting on it would be a very simple-minded model. Whereas Judith's not here, unfortunately, but the noise that's in the European Centre model is an additive stochastic noise. Well, I'm not sure that's necessarily consistent with that, actually. It's certainly not consistent with what you get in 3D turbulence. True. So relating it to this needs careful thought. That's a good point. I think the other idea or suggestion I'd make is that in 3D turbulence, this is the formalism you do to do a large eddy simulation, which is what I did earlier, and then you have to parameterize these terms in there. And there's a fantastic trick which has given lots of creative work, generated lots of creative work. There's a paper by Germano from 1990 or thereabouts, and his basic idea is to say, okay, we want to compute these interactions, and these are unknown terms. Can we use facts about the resolved flow to compute these in a mock way to tell us something about the real unknowns? That's extremely poorly put. What I mean is that we resolve down to some filter scale. We then subsample at, say, 5 times the grid scale to compute these terms explicitly, and then using the known scaling laws of turbulence in the inertial subrange, using Kolmogorov, which Joe told us about this morning, you can then use that to tell you something about your actual filter scale. Now, I was wondering about this in Tim Palmer's talk, but Tim Palmer was talking about convection, 3D turbulence with lots of other physics, projecting onto stream functions, as Emma just said. So there you've got to somehow get from a 3D turbulence to a 2D turbulence. But then this morning, Joe told us about another potential source of noise, I think, in the larger scale, which comes from the structure of the special kind of 2D turbulence we have in the atmosphere. So I guess I just wonder whether this idea may be worth thinking a little bit more about in some of these 2D turbulence as a thought. I guess my final closing comment, I'm overrunning now, so my final closing comment is it would be much more satisfying, obviously, if we could rationalize the stochastic forcing and point to terms and processes. We know a lot about atmospheric and oceanic dynamics. If the stochastic forcing can be more firmly rooted in a sort of more systematic framework, we'd obviously all be happier. And you'd hope, following the example of 3D turbulence, that thinking about it in these kind of ways gives you some steers on what the controlling dimensional parameters are, which perhaps we're missing. But I'm talking well out of my territory now, so I will leave it there, I think. Thank you very much.